Really?
Well, other professors that do just totally ignore the time limit.
Is that right? They just start whenever they want?
They start, and sometimes the video has a little bit of a break before the start.
Yeah. Okay, we're ready to go. So I hope you had a nice little break this Friday through the weekend. Let's see if I can remind you where we are. We're finishing up on linear viscoelastic models. So throughout the course, we've covered quite a bit of this book. We started by talking about Newtonian fluids. Then we talked about non-Newtonian effects. To talk about non-Newtonian effects, we talked about standard flows, and then material functions, and then finally, in Chapter 7, generalized Newtonian fluids. Now, the generalized Newtonian fluids were what we call inelastic fluids. They don't measure any time-dependent effects, any memory effects, any kind of elastic effects. Then we explored those quite a bit, and we saw that they can never produce the normal stress differences in shear flow and no memory. Then we moved on to these Maxwell models, and these slides are our old slides on our first model that can predict some memory effects. And we talked about the Maxwell model in both differential and integral form. Now, when we previously talked about Newtonian fluids or generalized Newtonian fluids, we could always do two different things when we had a constitutive equation. One is predict material functions so that we could see whether it's a good constitutive equation for what we're doing, whether it can predict behavior that we know the materials actually exhibit. And the other is to calculate flow fields. So the big picture, I guess, would be that we want to use these constitutive equations to calculate flow fields in flow simulators. So if you went and got a flow simulator like Polyflow, you might see choices for various generalized Newtonian fluids and linear viscoelastic fluids, and in fact, ones that we're going to work on in the future, upper convective Maxwell model, Odroid B model, all these interesting nonlinear models. And so what we're learning is what the differences are among these, how they got derived, and what are the trade-offs when you use one model versus another. So when we use the generalized Newtonian fluids, the main trade-off is no memory effects. Okay, there will be no memory effects in a generalized Newtonian fluid. And it has nonlinear effects because it does predict that shear thinning, but no memory effects. The main advantage of this model that we're currently talking about is its ability to predict some memory effects, but only in the small strain rate, small strain regime, which we haven't, well, we've talked a little bit about that, but I'll talk about that a little bit more here as I summarize. So with all of these models, we're trying to get into our heads how they behave. So we have justifications for why we created such a model, but the ultimate justification for using it is what it predicts. So this is what we need to know. These models, the Maxwell models, predict constant viscosity and zero first normal stress difference. It predicts constant elongational viscosity, and Troughton's rule, which is that 3 times the shear is equal to the elongation. It also predicts in step shear strain, it predicts something that is observed, which is exponential decay of the stress. And in startup, it predicts a gradual startup, which is also observed. Now, we did notice that although we do predict a decay, a time decay, it's not perfect, and so we worked on making it a better model, a better linear viscoelastic model, to get one that would fit the data much better. And so we invented the generalized Maxwell model by allowing there to be a variety of relaxation times and viscosities. So at the end of the day, we created a new model, which is a linear superposition of the original model, where we have, let's say, 3, in my example it's 3 different modes where there are 3 different relaxation times and 3 different adic sub k's. If you hypothesize that they just add up with no interesting cross terms or no other nonlinear effects, then you get this is the new constitutive equation, which has the same structure as the old one, except there's now a summation sign. So if I took this summation out and allowed the k to only be just one number, 0 or 1, that would be the Maxwell model again. So the generalized Maxwell model has the same structure of gamma dot as a function of t prime on the outside, this function of time integrated from minus infinity to t. It's a constitutive equation, so we can make predictions with it. And in steady shear flow, I asked you in the homework to predict it. And in step shear strain, I went through the prediction in class. So the answer for steady shear flow is that you have to add up the eta parameters to get the prediction of viscosity. And the answer that we got in class for the relaxation moduli was that you would get a sum of the same type of contributions that you get in the single relaxation mode. And then I showed you that this equation can be made to fit the data perfectly. Okay, so this is a very nice result. We can fit the data arbitrarily closely with a small number of parameters. So this is a summary of these models. This is the Maxwell model in differential form. This is the Maxwell model in integral form. And this is the generalized Maxwell model. Yes, one.
I was watching the video. I wasn't here last time, but as I was watching the video, I was thinking about those individual contributions for the viscosity. Would you be able to relate that to something like physically? Like, would you be able to, like, I was thinking, well, you have, you know, like, just have like linear scalars like adding to each other, and then you make up a new viscosity. Like, how would you relate that to like physical terms, like experimentally, like?
The different parameters in the Maxwell model physically represent, for instance, if you had a polymer, the longest relaxation time, we always draw polymers like these squiggles, right? Mm-hmm. Actually, we always draw them much simpler than they really are. They're really, really long, and there's a lot of squiggles. So if I drew it that way, we wouldn't be able to see much. But think of it as an incredibly long molecule with lots of squiggles. So if I simplify it and just say, well, there's my molecule, the longest relaxation time would be like the end-to-end distance moving on this molecule. So I have this entropic spring. We think of it in polymer science. So it's this random coil, and if I pulled on the ends, there would be a certain spring constant that is related to the effort it takes to pull on the ends. And that spring constant is the longest relaxation time. The friction that's associated with the whole molecule, that would be the viscosity parameter that goes with it. Okay. Now, what are the other modes? The other modes are like the half molecule, the quarter molecule, eighth of a molecule. So as you look at this big complicated mess and say, well, if I pull on the ends, I get one sort of big lethargic slow mode. But if I pulled on it halfway and then to the end, or on any subunit about the size of half the molecule, that would have a different relaxation constant.
So I mean, would that be like supported by studies? You know, like, so then if you had a monodispersed sample, then you would be able to fit experimental data with just a single, you know, like.
It turns out that monodispersed materials are not single relaxation time materials, but there are some materials, some polymer solutions that behave like single relaxation time materials. So it's not the polydispersity that gives you all the modes. You can have a monodispersed molecule, but within the molecule there are different relaxations that go on. So even if I held the ends of the molecule in place, there would be relaxations going on, right? There would be parts in here that would be finding a way to relax. If I held the molecule in place by the ends and didn't allow the ends to move, and then flow took place, the internal parts of the molecule would find ways of unraveling themselves and relaxing. And those are those shorter relaxation times. So the number of bonds that are involved is related to which relaxation time. So if you took a big molecule and really sheared it really rapidly, you would essentially eliminate the longest relaxation time because you're not giving it any chance to relax. It would just sort of stretch out, and you wouldn't be allowed to relax. But there would be shorter relaxation times that would be allowed, that even as you're shearing this thing like crazy, they would be going, they would be moving and getting out of the way of neighbors getting by. So there would still be relaxation going on, but they would be the shorter relaxation times that are taking place. So there is a real physics to it. And in fact, I'm not going to talk about it very much, so I might as well say it now. Our approach to constitutive modeling has been a continuum mechanics approach. We started with the Newtonian model, which is continuum mechanics. We started with the equations, gamma dot times mu, et cetera. But we don't have to start with the continuum mechanics approach. We could start with a picture of a molecule. We could start with a squiggly polymer like this. And so that would be the molecular modeling approach. So if I have a single molecule like this, and I'm saying it has a spring constant, then why don't I just model it as a spring? Okay? And maybe I'll put a bead on each end and say that there's some drag on these beads, and there's some relaxation mode here. And if I just did a statistics calculation, if I just put a whole bunch of these guys together and let them, depending on what my assumptions are, maybe they interact, maybe they don't, maybe I put them in a shear field, and just put in these kind of relaxation, these friction effects and these elastic effects, what kind of constitutive behavior would I predict? That's a different approach. It's going to turn out that the two approaches meet. Some of the models that we've predicted now can be predicted. We've predicted them through our sort of continuum approach. They can be arrived at through the molecular approach as well. So actually, nowadays, at the cutting edge of rheology, there's more work being done on molecular models than there is on the continuum mechanics models. But we still need the continuum mechanics formalism in order to be able to calculate flow properties. So it merges together at the end of the day. Thanks for that question. Okay, so we've created a model because we wanted to fit these data better. And the thing I wanted to point out here is that the form of the step strain prediction for the single relaxation model that's the form of the prediction. And this is the form of the prediction of stress relaxation in the multimode model. So for that reason, if we just put in a generic function and say, however your material behaves in the step strain experiment, you put that function here as a function of t minus t prime, and that'll be an even more general linear viscoelastic model. Okay, so this is a general expression that encompasses both of these two previous models. In order to relate them, we just have to specify what g is. So tau equals minus the integral from minus infinity of t of some function, gamma dot of t prime dt prime. This constitutive equation, the generalized linear viscoelastic model, has as its subsets the Maxwell model, where you let g of t minus t prime be eta naught over lambda e to the minus t prime over lambda. Or, so this is now Maxwell, or the generalized Maxwell, where you make g of t minus t prime equal to the summation k equals 1 to n of eta k over lambda k e to the minus t prime over lambda k. Or you could put any other function you like, as long as it gives you what you like to get as a prediction for the step strain experiment. So this generalized linear viscoelastic form is analogous to our generalized Newtonian fluid, which was stress equals minus eta, which is a function of gamma dot, times gamma dot the tensor, where this eta function is unspecified. And then we can specify it. We can say, okay, within this class, this is a class, this is a class. Within this class, if I specify eta equals m gamma dot to the n minus 1, then it's the power law. And if I specify eta equals mu, then it's the Newtonian. And if I specify that Kuro-Yasuda equation or the Dicke equation or any of the other complicated ones that we have a list of, we can get a whole bunch of different constitutive equations. So we're going to talk about the linear viscoelastic models mostly in terms of this general form, which we need to understand encompasses these two specific forms just as well. Okay, so that's where we are. Now I forget where I put everything. So that's not it. Yes, there we go. So now I want to do one more discussion of a prediction of the material function, because this one, the small amplitude oscillatory shear, is very, very widely used with this model, with the small amplitude, with the generalized Maxwell model or the generalized linear viscoelastic model. So there's a little bit of a derivation here, and I'm going to do it kind of quickly because I know it's kind of boring to go too detailed through a derivation, but it's really, I'm going to skip some of the calculus, but the derivation or the prediction is actually just exactly the same procedure that we've been doing. So the problem I'd like to discuss next is, for this generalized linear viscoelastic model, what are the predictions in small amplitude oscillatory shear? Okay. So we haven't ever done this prediction before, so this will be different for us. So I'll start by saying that I'm essentially addressing the question, how do I use the generalized linear viscoelastic model? And the answer is the same as any constitutive equation. 1, predict material functions. And 2, calculate flow problems. So let's do an example. Predict G prime, G double prime for the generalized linear viscoelastic model. Okay, so let's try to do this together so that I think you'll benefit more from doing it. How, and again, you've never done this kind before, but it's not that different from before. We've got this sheet which has the kinematics and the material functions on it, so we're just going to proceed. So how should I start to be able to predict the small amplitude oscillatory shear material function? I'll write the equation down for you. Stress equals minus the integral from minus infinity to t, g of t minus t prime, gamma dot of t prime, dt prime.
You look at the shear tensor and see how it, how
Yeah.
it simplifies.
We need gamma dot, according to this equation. We need the stress. You see, here's the stress we're looking for, tau 21. So we need to predict tau 21. And we're going to predict it from this constitutive equation. And G is a parameter of the model, so that can appear in our answer. Gamma dot is what we need from our specific equation here. And here we have V, which we can relate to gamma dot. So that's been our standard procedure all along. whenever we predict a material function. So we'll start with gamma dot, del V plus del V transpose, which we've done many times for shear flow. 0, sigma dot, 0, sigma dot, 0. And I'm already writing it in terms of T prime, because that's the one we need. So for starters, there are no normal stress effects as usual. And so we can immediately write our stress constitutive equation just in terms of tau 2,1, which is the one we want anyway, which is just got the sigma dot tensor function there. Minus the integral from minus infinity to t, g of t minus t prime, times sigma dot of t prime, dt prime. From here, it's just calculus. Okay? From here, it's just calculus. We've done all the rheology. Okay, so sigma dot is given in the material function. So we'll put it into the equation. And we have to carry out an integral. Once we finish carrying out that integral, we have to somehow relate that to this definition, which is a little weird. All of our other definitions have been very simple. Take tau to 1, divide it by something, and that's your answer. This one's a little weird. We're trying to predict g prime and g double prime. And there's these sines and cosines. Not entirely clear what's going on, but it's going to work out. Okay, so let's plug this in. Tau to 1 equals minus the integral from minus infinity to t, g of t minus t prime, times sigma dot, which is a constant gamma dot naught, times cosine omega t prime, dt prime. So notice that this is sigma dot of t, and so everywhere there's a t, I put a t prime. So gamma dot naught cosine omega t prime. Now, there's a little, it's not exactly a trick, but it's a little convenience that we often use in these integrals. And that is we define a quantity called s, which is equal to t minus t prime. So let s equal t minus t prime. And this is not necessary. You could do this integral without doing this. But this is most often how you'll see it in my book and also in other places in the literature. So let me just rewrite this as t minus t prime here. So if I let s equal t minus t prime, then I have to look at my limits here. When t prime equals minus infinity, what's s? Infinity. When t prime equals t, what's s? 0. So it's the integral from infinity to 0 of g of s, gamma dot naught, which is a constant, I can move that out, cosine omega t prime is equal to t minus s. Now dt prime, ds equals, this t is a constant with respect to this integral, so it's minus dt prime. And then there's a minus sign. So let me just rewrite that because it looks a little sloppy. Tau 2,1. Integral from infinity to 0 is kind of backwards. I'm going to flip the order of integration, which means I have to put a minus sign. Integral from 0 to infinity of g of s. I'm going to take this gamma dot naught over to the other side. It's just a constant. Cosine of omega t minus omega s ds. Okay, so again, we just need to now do this integral. And what I'm going to do is I'm going to split this up because this is the sum of two angles. So I have this identity from trig cosine of A minus B is equal to cos A, cos B, plus sine A, sine B. So I can use that to split up that integral. So I'll move this minus sign over to the left so I don't lose it. Minus tau 2,1 over gamma dot naught equals two integrals. Well, let's see here. Okay, I'll do it all together first. Integral from 0 to infinity of g of s times. So this is cosine of A minus B is equal to cos A, cos B, plus sine A, sine B. Now I'm going to break this up into two integrals, and the omega t part is not a function of s, so it can be brought out of the integral. So this cosine omega t can be brought out of the integral, and this sine omega t can be brought out of the second integral. Okay, so there'll be two things I'll do here. So I have the integral from 0 to infinity of g of s cosine omega s, and that's times cosine omega t, plus the integral from 0 to infinity of g of s sine omega s ds times sine omega t. And believe it or not, we're basically done. We're basically done. We don't know what g is, that g function, until we say we're talking about the Maxwell model or the generalized Maxwell model. And look at how our result has turned out. It looks very much like this material function here. It's something times sine omega t plus something times cosine omega t. I'm going to do a little bit more algebra here. First of all, look up here. Gamma dot naught is equal to omega gamma naught. So that changed, that's right here, omega gamma naught. So I have minus tau 2,1 over gamma naught, not dot, gamma naught omega equals, now I'll just do this to emphasize what I said, something times cosine omega t plus something times sine omega t. When I compare that, this first something with the cosine, that must be g double prime. Or almost, because my left-hand side is minus tau 2,1 over gamma naught. So I need to move the omega off to the left. So what I really want on the left-hand side there is minus tau 2,1 over gamma naught. So now that's equal to something times cosine omega s plus that other big term, sine omega s. And this term was integral from 0 to infinity g of s cosine omega s ds. This one was integral from 0 to infinity g of s sine omega s ds. And so these have an omega out front, and it's the same thing. Omega times the integral from 0 to infinity g of s cosine omega s ds, and omega times the integral from 0 to infinity of g of s sine omega s. Did I forget something?
I just put s instead of t's on the outside. Cosine omega t.
You're right. Thank you. These are omega t's. Thank you. So for any generalized linear viscoelastic model, I can calculate g prime and g double prime. So the one with the cosine is g double prime, so this is g double prime. And the one with the sine omega t is the G prime. And so I get G prime is equal to omega times the integral from 0 to infinity of G of S sine omega S ds. And G double prime is equal to omega times the integral from 0 to infinity of G of S cosine omega S ds. So it really worked out very similar in many ways to the other predictions of material functions. And in a very straightforward way, we can calculate predictions for G prime and G double prime for our models. So for instance, for the Maxwell model, we know that G is equal to, this function G is equal to eta over lambda e to the minus the variable over lambda. So when it's G of t, there's a t here and there's a t here. When it's G of t minus t prime, there's a t minus t prime there and there. And when it's s, there's an s there and an s there. For the generalized Maxwell model, G of s is equal to the summation k equals 1 to n of eta k over lambda k e to the minus s over lambda k. This function g is the function that appears when you do the step strain experiment, and it's the function that appears out in front of the gamma dot in the generalized Maxwell, in the generalized linear viscoelastic model. Now, to get from here to these predictions, you can see that you have to do a couple of integrations. So if I put this one in, I put an integration, I get an integral of an exponential times a sine, which you can do on your calculator or in MathCAD or look up. Or you can do it by hand if you remember how. It requires 2 integration by parts. Okay, it's not that tricky, but it's, you know, a little tricky. And you can get an answer. And the same one here, you get an exponential times a cosine. If it's the sum of the exponentials, you get a sum of those things. I'll just write the results down because these are very useful. For the generalized Maxwell model, they turn out to be G prime is equal to the summation k equals 1 to n of G sub k lambda sub k squared omega squared 1 plus lambda sub k squared omega squared. G sub k is lambda eta k over lambda k. G double prime has the same denominator, 1 plus lambda sub k squared omega squared, the same summation. The numerator, it doesn't have the squares. Gk lambda k omega. Can you tell me, as omega goes to 0, what does this function approach? What does this G prime approach? This omega goes to 0. This becomes very small with respect to 1. Denominator becomes 1. So it becomes the numerator, right? So with respect to omega, G prime goes like omega squared. Does that sound familiar? Okay. How about G double prime? As omega goes to 0, this goes to 1. This goes to 0, so this goes to 1, and it approaches omega. So these functions predict what really happens in the terminal zone. That G prime goes like omega squared, and G double prime goes like omega as omega goes to 0. Check. Very, very good prediction. Very good prediction. So here on the slides are these results. Here are the generalized linear viscoelastic results. Here are the generalized Maxwell results. And this is what these functions look like. Okay, you can go into Excel or MATLAB and just evaluate these functions as a function of omega, put in some value of g and lambda, and you'll get a function that looks like this. This is a shape I'd like you to remember. This is a very useful shape. Here's my slope of 2 and my slope of 1. Okay? The g prime goes up to a plateau. That's familiar too, right? This is the entanglement plateau that we saw in our data. Now, it doesn't show the other part, where things go off to infinity later, but it predicts the terminal zone and the entanglement plateau. It predicts the terminal zone of g prime, and it predicts the reduction. Now, actually, usually it comes back up eventually, but it predicts a whole lot of the actual linear viscoelastic behavior of materials. Now, what happens when you get to the summation, where you have multiple versions? Well, you're going to add a whole bunch of this kind of functionality together. Now, let's take a look at this, for instance. This point right here is an important point. Notice how I've plotted the data here. I've plotted it dimensionlessly, and it's plotted versus omega lambda. Omega and lambda appear together. Omega lambda there, omega lambda there. Okay? This is omega lambda equals 1, which is omega equals 1 over lambda. Okay, so the cross point, this is worth remembering, the cross point of g prime and g double prime is when omega equals 1 over lambda. So if I compare this data with, let's try it. I'll write an exam question here. Okay, if I have this on a log-log scale, log g prime, g double prime, log omega, and I draw g prime, g double prime. Okay, this point is omega equals 1 over lambda of that model. So if I ask you, please sketch for me a material whose relaxation time is twice as large, what are you going to sketch?
The omega will be twice as to the, well, in a log, I don't know how it would show in a log scale.
Well, is omega twice
Yeah.
if lambda is doubled?
No, it's the half of it.
Right. If you double the relaxation time, then the omega where the cross appears is half. So it shifts to the left. This point shifts to the left. It's actually, this level is equal to g, which is eta over lambda. So it's also going to affect that level as well. So I would have to phrase my question very carefully. Am I saying a constant value of g that lambda changes, or a constant value of eta that lambda changes? But that's the idea. This whole curve would shift to the left when you increase the longest relaxation time. And remember, you saw that too. Do you remember in the chapter on the material behavior, when we looked at g prime versus frequency, we had some curves that look like this and curves that look like that. And I asked you at the time, which material, A or B, has the longer, is the higher molecular weight? Which is it, A or B? A. Why?
Because the plateau is broader.
Broader plateau, higher molecular weight. So now that you know this about relaxation time, what else are you seeing?
The relaxation time is bigger, so it shifts to the...
Right. So you see the relaxation time shifted to the left as well. That's what this is telling us here. This knee in G prime shifts to the left as the relaxation time gets longer. And that makes sense too, right? As molecular weight gets bigger, relaxation time gets bigger. Okay, so it's all working very nicely. We're actually relating material parameters like relaxation time to the rheology. Okay, not just, when I taught you this, it was just an observation. But now it's matching our models. Okay? So A has a larger molecular weight and a larger relaxation time. Now, if your data don't look exactly like this, you can use the generalized Maxwell model to fit it. Here's an example where I have fit some data that do show a terminal zone, but they don't show much of a plateau modulus, and then they also show some more stuff going on at higher frequency. And what I did to fit this is I used the generalized Maxwell model equations, and I went into Excel and used Solver. And Solver is just a nonlinear curve fit program. All I did was I created a prediction, subtract the prediction from the actual data, and asked it to minimize the difference between the two. And look, I can get a really good fit of the data. Now, there's a handout for how to do this on the website. And in classes past, I've shown people how to do this, but I'm going to skip it this year. We do it in the Rheology lab class that's offered in the fall if you want to learn it, or you can try it out on the web, and there's even a trial Excel program on the web you can take a look. There are a few tricks involved. And in fact, it's also described in the book a little bit, because with any nonlinear curve fit, you're better off with a really close first guess in order to get a good fit. But you can fit anything with 10 parameters like that. You can predict very well. Here's some data where, I don't even know how many, maybe 10, maybe 20 parameters. 1, 2, 3, 4, 6, 11. Looks like 22 parameters, but a darn good fit. You can fit any strange data that you like. One of my points in discussing this data is, though, that the data are going to make a prediction in both of these cases. They predict the longest relaxation time, which is a number very interesting to us, because this is the amount of time, in this case 4,000 seconds, the longest amount of time you would have to wait for all relaxations to take place in this material. And this number is basically fit by the terminal zone. These are the long relaxation times. Remember, we talked about everything moves to the left as you have longer and longer relaxation times. So these are the longest relaxation times of your material. And so the part of the curve that's fit by the longest relaxation time is the terminal zone. In this case, the terminal zone is actually seen. There's a slope of 2 and 1. In this case, these are not quite slopes of 2 and 1 where there's data. It becomes slope of 2 and 1 just outside of the range of the data. So this is actually something of a false longest relaxation time, because we really don't have data out here to say whether we're truly in the terminal zone. Also, at the high frequency end, the data only fit as long as you pick a relaxation time that's similar to 1 over where there is actually data. So for instance, the data here stop at about 10 to the third. So 1 over 10 to the third is the longest relaxation time that we can report. I mean, excuse me, the shortest relaxation time we can report. These relaxation times are needed in simulation programs. In simulation programs where you actually use even the nonlinear models that we're going to discuss next, you still need to know the predictions of the model in the linear zone, and that's what these relaxation times tell you. Okay, so that's as much as I wanted to discuss this chapter on generalized linear viscoelastic models. And this is a summary of what we've learned from these models. They all predict a constant viscosity, so we have not improved our ability to predict nonlinear viscosity. They are limited to, for instance, the generalized ones are limited to where strain is additive, because we added up a stress contribution for each of the relaxation times. We added up the contributions one on top of the other, and that's only true in the small strain rate region. We've seen that with these models, there's the gamma dot tensor, And so the gamma dot tensor in shear flow is sitting right there in our equation. And therefore, when we put them in shear flow, they'll never predict shear normal stresses. So we haven't improved that. And they also have an additional problem, which I'm going to talk about, which is they do not properly predict flows with a superposed rigid rotation. Now that seems a little obscure, and that's because it is a little obscure. But it's actually the clue to how to improve from where we are right now. Okay, so that's what I want to discuss next is, are there any predictions of this model that are complete garbage? Okay, and the answer is yes. All right. This is the example where I can show you that there are predictions of this model that are complete garbage. And this example is worked out in detail in the text, and I can also give you a copy of the algebraic details. But I think I would just put you to sleep if I did this entirely in class. But I want to explain it to you so that you can appreciate what we're talking about. Okay. This is an example that was devised by Bob Bird, in his book, Bird, Armstrong, and Hassiger's book on dynamics of polymeric liquids. And it's a way to demonstrate that there are some flows that when you put this model, the generalized linear viscoelastic model, and make a prediction, you get garbage. And the kind of flows that give you garbage are flows with a superposed rigid rotation. So this would be, imagine this is a hunk of fluid. If I just rotated it in place, the stresses aren't changing. Let's say it's a piece of Jell-O. The stresses aren't changing. I should predict the same stresses in the material. Let's say I gave it a little bit of a stress, but just held it, and then just rotated it around. The stress doesn't change, right? It should be the same, independent of this rotating. So if I put my hunk of Jell-O on a turntable, so that used to be a good analogy. Now nobody has a turntable anymore, and a CD player doesn't quite work because you don't see it spinning. But you know, you have to put it on a Lazy Susan, I guess. If you just put it on something and spun it, okay, slowly. I'm not talking fast. I'm not talking inertia. I'm talking really slowly maybe, but I am rotating it. I should calculate the same stresses on that material. Do you agree with me? There should be no difference in the stresses just because I'm rotating the table. Okay. There is in this model. Okay. There are extra stresses. In fact, as I'll show you in the derivation, just when I flash it by you, you predict with the generalized linear viscoelastic model, you predict that depending on the speed of the rotation, the stress is different. Okay. It's a problem. It was noticing this effect that led people to fix the generalized linear viscoelastic model, and that will give us nonlinear models. Once they're fixed, once we fix this model, we're going to get a model that predicts normal stresses in shear flow. Okay? We're not going to guess. We found a problem, this superposed rigid rotation problem, and when we fix it, we're going to get a model that will predict normal stresses in shear flow. So let me describe that prediction, and I'll flash it by you on Wednesday. The idea is that there should be no change in frame of reference. If I, for instance, in this example that I'm going to discuss, if I put a shear flow on a turntable and try to describe that flow from a coordinate system that's sitting on the turntable, and then separately try to describe that flow from a coordinate system that's sitting off the turntable, I should get the same stress. Now the math won't be the same in between. The math will be quite different. The one that's on this slowly moving turntable on top of this table will look just like every other calculation we've ever done, because you're sitting on the table, you're rotating with the flow's doing shear flow. You could care less that the turntable's moving. It's not moving fast. We're not talking about Coriolis forces or centrifugal forces. Moving really slowly. That prediction you can all do. That's the regular prediction of shear flow. The more complicated one that takes a bit of vector transformation of coordinate system is to calculate the same viscosity, calculate the viscosity of this fluid, but use this coordinate system, a coordinate system that's stationary. So now I'm looking at this turntable and the thing's moving like this, very slowly, but it's moving. So my description of where each fluid particle goes has to follow them as they rotate around. A little bit tricky. So like I said, I'll flash that by. We're not going to take the time to go through it super in detail, but I'll flash that by on Wednesday. And what we'll see is that it predicts that the viscosity is a function of the rate of rotation. Okay? And then I'm going to talk about why that is. And the reason is it's because of strain. Okay? The strain that's being measured in the rotating takes it mathematically into account as if all that rotation was producing strain, which it's not. Only this is producing strain, not this. And when we finally find a way to describe strain properly without the rotation, we're on to nonlinear viscoelasticity. So we'll start that on Wednesday.